We are living through a revolution named after a paper, but it is a software-only miracle. While artificial intelligence can write poetry and code in seconds with breathtaking fluency, our physical robots still struggle to pour coffee without spilling or open a jar of pickles without crushing the contents inside. The bottleneck isn't that we lack smarter algorithms, it is that we are trying to download human-level digital reasoning into bodies built for the industrial age, or worse, toy-grade actuators. We have brains that can think in nanoseconds, but no bodies capable of executing those thoughts in a world governed by friction and gravity. The story begins with the architecture itself, often called "attention is all you need." Since 2017, this transformer model has dominated artificial intelligence because it solved sequence processing using self-attention mechanisms that ignore physics entirely. In the digital realm, these models deal with tokens, which are abstract symbols without mass or volume. A token for a cup of coffee is just as easy to process as a token for a mountain range. There is no gravity pulling it down and no friction slowing its movement across a screen. This success creates an illusion that intelligence can simply be scaled up until robots become human-like. But the moment you try to apply this digital logic to physical matter, the disconnect becomes glaringly obvious. We are facing what researchers now call the embodied intelligence gap. While text models learn from infinite data streams of human language found online, physical robots are starving for specific labels required to understand how their bodies interact with reality. Current datasets fail to capture the critical details of contact events and failure states needed for robust training. Unlike images or text where a million variations exist in digital archives, every single trajectory a robot must take is physically executable by a specific mechanical body. This means that capturing force signals and contact data in real-world scenarios is incredibly expensive and difficult, creating a scarcity where software abundance meets hardware starvation. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The stakes of this gap are visible whenever a robot attempts a simple manipulation task. Software might predict a path perfectly based on visual input, but the actuator lacks the precision or feel to execute it without crashing into an object or slipping off a surface. While standard self-attention mechanisms focus on reducing computational latency from quadratic time complexity to linear speeds in silicon, there is no corresponding breakthrough in mechanical design that allows these smart brains to handle complex physical tasks with human-like dexterity. We have abundant behavioral data from the physical world, yet we lack any mechanism to convert it into usable supervision for robots. This disconnect means that even if you train a model on terabytes of video showing humans performing tasks, the robot still does not understand how much force is required or what happens when an object deforms under pressure. The reality check comes from understanding that current research focuses heavily on making algorithms faster rather than building better bodies. We are optimizing for speed in computing, but ignoring the fundamental limits of actuators and sensors. The hardware lag means we cannot simply download a humanoid robot into our homes tomorrow because the mechanical execution layer cannot keep up with the speed of digital reasoning. Robots remain specialized tools that can perform one task repeatedly, rather than general-purpose assistants capable of adapting to the uncertainty of a changing physical environment every second. This is why you see robots in factories moving heavy objects on fixed paths, but failing miserably at unstructured tasks like folding laundry or navigating cluttered living rooms. The path forward requires more than just scaling vision. Language action models. It demands entirely new mechanical designs and sensor fusion strategies that can handle the nuance of matter interacting with matter. We need what some call a transformer for mechanics to match the sophistication we have achieved in language processing. This involves developing auto-labeling interfaces, embodiment retargeting systems, and world models that explicitly understand physical constraints rather than just statistical correlations between pixels and actions. Until we bridge this gap through breakthroughs in actuator physics and mechanical design, robots will remain confined to controlled environments where the variables can be managed by software alone. The future of robotics isn't about smarter code, it is about the hardware finally catching up to the intelligence that has already arrived. We have abundant behavioral data from the physical world, yet no mechanism to convert it into usable supervision for robots. Current generative AI cannot bridge the gap between digital reasoning and physical execution without breakthroughs in mechanical design and actuator physics. The future of robotics isn't about better code. It is about the hardware finally catching up to the software that has already outpaced our ability to build bodies capable of using it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.